And it's trying to get the thing on the screen. That's about probably as good as I'm going to get it. Okay. This is the permit sheet called Floorplan. It's a mandatory sheet. 6 of the sheets are mandatory, and this is just one of them. I don't think that all the stuff that's on this page is necessary. I think they're interested more in where the walls go. But this one, it looks like it was just had the page filled up, so it wasn't a lot of blank areas. I did fix the toolbar. And now we're in business on that. Okay, this is the structural frame that's under the floor. It shows columns, top and bottom tie beams, the foundation pads. There's also a 3-inch pad poured under the foundation pads. It's a minimum of 3. It could be 18 some places. The deal is I don't want to build on disturbed soil. So we dug it until until we got at least to the 6 feet of depth for those piers in the ground. And then any of them that went over that, we didn't throw fill back in it. We just shaved them with a square point shovel till they were level. And then we went around with the transit all this, within 10 minutes, without resetting it basically. We drove a rebar in the center of each one of those holes, set to the 6 foot deep. And then we went around and just poured concrete, no rebar or anything, just like if you were putting gravel in the bottom of one of these holes, except we wanted something solid because the rebars have to stand on something. And if it's gravel, it's just going to sink right in and lean over. You spend your whole life... See, the forms are kind of heavy when you set them up, and the rebar's a little heavy. But you fill that thing with 2 tons of concrete, and whatever you had holding it upright, there's a good chance it's going to shift. So we do undisturbed soil, and then we went in and put a piece down under each of them. There's one that's probably... That's on the screen. I don't know if this is all locked together. Yeah, it's grouped. We're gonna do a thing about what's inside of these columns and how much rebar it is, and how the rebars are bent, and the size of the stirrups and all that, and the placement of stirrups. But the basic thing here is just showing you a false bottom in the hole with a piece on it, and then these uprights. This bar is bent 90 there and 90 here, and then the rest of the 20 feet goes straight up. And there's about 14 or 15 inches of it sticking out of the first roof slab. The rest of it's used up going down into the ground under the house, and then this curved thing. Anyway, that's what's under the floor plan. Moving over. This drawing here is labeled hollow block layout of walls. This one is showing the walls of the floor plan, but no columns or tie beams, top or bottom, or anything else, only the blocks. I mean, how much of the house is made out of block and how much is not block? And of course it leaves door openings, which you may not have visible in other views. This is the one that the fire department rejected. We had to basically reprint everything, and we moved this wall over and we moved that wall over, and then we had to put doors in any place there wasn't a connection. Where are we? That's the stairwell room. So this is bedroom 2, 3, and 4. And then we got 2, 3, 4, and 5. Because there's a master bedroom over here. And this is the master bath. So master bath, master bedroom, stairwell, bedroom 2, bedroom 3, bedroom 4, and bedroom 5. And these will show up in another couple of drawings. This is a CR. And this is a wall that was later done away with. The idea is that if a line of sight into the room and the CR and stuff, you can't see the way there's a door here and there's a door over here. This goes into the atrium, this round thing here. And those doors are misaligned so that if you look through that door and through this, all you can see is the end wall of the CR. So basically, if you don't have any doors at all, just openings for doors, the room is still private. And that lets us have air circulation all we want. But anyway, this was drawn to be hollow blocks. And they can count them. You know, the drawings are really big. They're much bigger than what's it's zoomed out to here. But it just, that part of this floor plan drawing shows that. This is it's the original rendition of ceiling beams and stuff for the roofing. This is roof, and this is the slab that's above the first floor. The first floor would be down here, and this is the roof, and this is the cupola in the middle of the roof. We basically lifted this top slab up 24 inches, and of course it's not as big. It's over in here someplace. Looks like a wedding cake, and it will really look like a wedding cake when we put our wind turbine, vertical axis wind turbine, up on the roof. It'll look like the figures on a wedding cake. Come down the road, we'll say just go to the wedding cake house. Anyway, these walls here are reconfigured to be more earthquake resistant, and I don't think they'll object to that. I didn't clear that with them, but I don't think there's a problem. Everything else is right, you know. Okay, so this here was replaced by no beams in the quadrants. They're done away with altogether. Like these beams here, we could have cast a 3-inch thick floor slab and some support beams. But basically you form up the support beams and then you put a piece of plywood or something over the part that's not support beam. So you're pouring this and then it runs down into this. So the beam down here is basically going the height from the bottom of the beam to the top of the floor. You'll see that in other people's videos. It's easier to see it than to try to explain it. We opted not to have to form all these little forms and things. We come back out here to the end at the atrium end. We made the floor 8 inches thick there, 6 inches thick out here. It's 2 inches of slope in 24 feet. And for rain drainage basically. Was less rebar, way less forming. It was just a better deal for us. The concrete was cheaper than the complexity. And it's looking like, we could reuse some of these forms. I don't know if we could have made them last 10 times though. So we probably would have got 3 pours out of them before they got ratty and they had to do them over. So we did away with those. You just went with a thicker slab. Now, when you're figuring how you're going to support a suspended concrete floor, you do structural analysis, and it is simple enough that a high school kid can do it. You take a 1 meter wide strip across the short dimensions of the room. Would be where's my mouse? It would be worst case is over here. You don't keep this The support of this wall is not included in calculations. It's like the slab was there with nothing underneath of it for when you're calculating it. So we take a 1 meter wide strip across here. We figure the concrete in that strip at a 160 pounds to the cubic foot, and where steel is 480, concrete's 160, and rock, that's about the same thing. Wood's like 60 to 80, depending on species. But anyway, you figure out what this this strip of concrete, because we're working in metric, I just chose meters. I could have made it 1 foot wide, doesn't change the calculation. Just all the units have to be the same kind of measurement. So what you do is you go half the distance of that length, and you take half of the total weight of the strip, and you say that's the load pointing down. That's what you're trying to break. Okay, so if you take the height, which is the thickness of the floor, if you're doing a 4-inch thick floor, which is really typical, you go from the surface of the concrete down to the depth of the rebar. Not the bottom of the concrete on your test strip, but to the bottom edge of the bottom rebar. Now your stirrups will be down below that a little bit because they're three bar diameters of a number 10 bar off of the bottom of the floor. Well, actually, there's no stirrups. They're just left and right and front to back bars. We're not talking a beam. It's done like a beam calculation. That's what's confusing. But we're doing a floor right now, so no stirrups. Just bars 90 degrees to each other. Now, if what you do is the lever arm of a torque is from the top surface of cement down to the bar that's going to carry the load. It comes out inch pounds usually. If your strip of concrete was in pounds and the depth that you're using went down is in inches, then you get inch pounds. Now, that's how much load is trying to break that strip or break the beam if you're working with a beam. So you have to counter that with steel, which is to the tension side. So you say, okay, this is 420,000 inch pounds or something like that. And if I have steel that's 65,000 pounds per square inch, you know, figure the shabbiest rebar that they can sell over here, and that's what you figure the strength on, because you don't know what you're going to get. The labels are insignificant. Plywood with no glue, hollow blocks with no cement. You buy steel, it's you have to pay for about 1.5 times the thickness. It's all right as long as the quality of the material's there. However they set the price, it just ticks you off when you first start dealing with it that you're paying for the 3/8 flat bar, and what you get is 0.162 instead of 0.375. But once you realize it, and when you go for a reorder, you carry a scrap piece of what you had and says, I want this stuff no matter what you call it. And the first time you go back in the steel racks and put your finger on the one you want. And then they'll go to the office and then they'll look in a book and they'll get a price. They're going to give you a dimension. Don't let it piss you off. It's nothing mean intended in it. It's just the way it works. Anyway, so you figured out how many, by dividing the 60 kips of strength on the rebar into like the 430,000 inch pounds, you find out how many square inches, directly, how many square inches of steel has to be there to counter that load. So now you can divide that steel into number 16 bars, and you can divide it into number 12 bars, and probably nothing less than that on a 4-inch slab. And 18 is, they're so far apart that you haven't got good grip strength between the concrete and the bar. So what we did on our suspended slab was number 12s. Now once you decide that, then the catalog or Wikipedia will tell you the equivalent square inches of a number 12 rebar. And that times your 60 kips, that'll tell you how many rebars you have. You can't, if it's 59.9 of something, you have to go up to 60. You can't make it 59 or 58, okay? Because that's the exact minimum steel you can use. So you come up with how many bars. Generally, you're gonna calculate it 3 times. Once with the 1-2 light, and once with 1-2 heavy from what you're figuring you want to use, or what you've seen other people use, or what's in some kind of design guide, or whatever you're trying to rough it in with. But you're gonna calculate 1 heavier and 1 lighter. Now, because it's the same number of square inches, a bigger diameter bar has a lot less of them. And that means they're a lot farther apart in the floor. Also, a number 16 bar compared to a 12, the little upset, what do you call it, deformed ribs on a rebar, that's what you're trying to pull through the concrete and try to make slip to make a failure. So anytime you can increase the area of those little ribs, it's going to be to the good. You're spreading the load over the floor and over the rebar. So I generally opt for, I could have used 16s on this floor. They were right in the calculation. And 12s actually probably took 1 more bar on the crosswise direction over the entire width of the slab. Hardly any difference. It's just a square, where the square inches divide into how many bars you have to have. So now you know what it would take for the minimum. Now you have to change the second run through on the calculations. Is once you've decided what size of bar you want, what kind of safety factor you're going to put into this building or slab or whatever. Standard on this kind of stuff is 1.5. When I do like an aerobatic airplane, I'm working with 6 negative and 9 positive, sometimes up to 12. Unfortunately, you can't build a structure for a race plane that's down to that strength. Because if you're working with fiberglass, Kevlar, S2 glass, carbon fiber, there's all kinds of materials you can use for the fabric. People tend to tap on it on the runway. They tend to tap on it in a hangar when you're not there to see how stiff it is or how strong it seems to be. Like they could rate it by beating on it, but they do that. And they can delaminate your core from your wing skins or whatever with no malice. They're just, misinformed. Writing "do not touch" doesn't help you. You have to have an armed guard 24 hours a day. So you lock up the race plane so people don't do that. But because of the people damage and children's damage and people piling stuff on top of it, a big heavy box of parts while they're trying to read the label, it's just endless. You can't build it that thin or that light. So you end up going for a number of layers of composite that is damage resistant from people. And when you do that 12G airplane, it now weighs 400 pounds more on the whole airframe. And it's a 27G airplane. A human being that pulls on the controls hard enough to get past 9 is a brave son of a gun. He'll never get to 27. He'll be dead before he gets there. But he can yank back on it all he wants. Well, on this, we want to have a load factor of more than the 1 that we're calculating. See, that's how I got off on a tangent. I do that. I'm sorry. You can complain in comments because I'm not going to edit on these first dozen things. I'm just going to try to get anything posted that somebody might could use. So we're going to pick a 1.5 safety factor. So that weight that you used on your test strip, because you've probably adjusted your test strip up and down with different moments. The torque values are called moments. The distance of the surface down to the bar. You've probably adjusted your floor a little bit this way and that, and figured out how many bars you had to have. And if you go thicker on the floor, that increases the distance, the lever arm of your moment. And that means the steel it's more resistant to the breakage and bending. So that's why you keep changing the dimensions of everything while you're playing with it. I started off calculating a 4-inch floor, and I went with a floor that was 8 inches at the hub and 6 inches at the edge. And that was my best compromise, strength, minimum materials and all that. And then that's at a 1.5 safety factor. And that gives you a different bar spacing, which is better. And that we call that dead load. It's the load that just lying there dead. It doesn't move. It never changes. It's just there. Then you have live load. The live load, you pick a number. This is for people walking across it. Furniture, refrigerators, tables. The boxes of stuff that you couldn't find anywhere else to put in your other house. You just piled them in some room. Whatever it is, a good working number is 50. If you was in English systems, because we're using inches and pounds, you would be using 50 pounds per square foot of area. So that 50 pounds per square foot plus the 1.5 safety factor multiplied by the actual weight of your tissue strip, and then you can calculate it. That's the last time. You only have to do it that many times, and then you're good to go. It's a simple calculation, and the only complex part is you keep trying different combinations of floor thickness to change the lever arm length, to change the amount of steel. And when you're doing the steel, you want to go the maximum little gripping ridges on the rebar, maximum square inches that it has to pull out of. That's why you tie your splice rebars with like 4 tie wires instead of just 1 or none. It's because you can get those ridges to interlock with each other, which makes it much stronger than the individual bars. Anyway, that's another tangent. Where are we? We're doing this is a thing on the floor plan for building permit. And I got as far away from that as a human being can. Let's go. Have to wake the computer up now. Oh, it's gonna save the drawing. You gonna let me do it? Maybe not. It was thinking. Huh? I'm going to pause for a second. No, I'm not. No, I'm not. Don't lie. Okay, this is the part of the floor plan that the fire department wants to look at. This is labeling the rooms, and they're going to look for egress out of the building and things like that that fits a list of requirements. And it shows that a queen-size bed will fit into the room, but I don't really think that you have to have furniture. It just makes it easier for somebody to visualize what kind of a room in the house is. Like up here, all these drawings are 3D. If I looked at it in perspective, I'd have walls. But this is a sink, a toilet, or a urinal, a shower, and a bunch of floor space. But they might want to like sanitation wants to know how much pipe is going to be under the building, and is it accessible if you break it. So they might be looking at this, where the fire department is looking at how you get out of this room if you manage to set concrete on fire. Of course, you'd be a rich person after that, because people would be interested how you could screw that up. It's got the same title bar as on the last several videos. I think this is going to be like 3 videos to cover 6 sheets. One of the sheets, and all of them can have another column over here, and it would be divided, and it'll have the like civil engineer, underlined place where to sign it, and a place that they can put down their serial number, on their license, and the date the license was issued. And the one that goes to the mayor, it's basically the cover sheet for the stack. There's an order you stack them up in when you roll them up to hand them in. I'm kind of thinking the perspective one on top, but don't hold me that. I got no clue right this time, because it was a couple years ago. But this organizes the people's names and makes sure there's something written in every block. It's a one source thing. Okay. I believe in it. As nobody will think I haven't beat this to death. Okay, end of video, pretty much. If you found anything helpful here, click like, or not, but you can. And if you think other than going off on tangents and being repetitive, the tangents are inadvertent. The repetitive is some points are important, and just want to make sure that I got it in there. So it's semi-intentional, but the rambling, that's just what old people do. You get in your 70s, you'll do it too. Okay, so we're gonna close this thing, and if you're still watching this and it turns out to be a series, I'll be back in a little while.